Hello, everyone. I hope you're all doing well. Today, we're going to start on Chapter 8, which is all about bivariate correlational research. And so this chapter is going to focus on sort of two major portions. We're going to start by talking about bivariate correlations and what they are, and then we're going to start looking at how we can interrogate these association claims. So evaluating the types of claims in our four validities that we've talked about before, but how they specifically apply to these types of correlations. So if we're talking about bivariate correlations, well, what are they? So these are going to be associations that involve exactly two variables. So bi meaning two, variate for variables. We will look at in the next chapter multivariate correlations, where we're going to be having more than two variables. But for now, to just sort of dip our toes into the idea of correlations, we're going to look at two variables at a time. Now, just for an example of what we might be looking at for a bivariate correlation, we have a couple of examples. So here we have some sample data from the MEL study on well-being and deep talk. So this is from an earlier chapter where they were looking at how did people report on their well-being, how well do they think they're doing, and how often are they engaging in sort of deep emotional conversations. And so this is just the raw data looking at person A, B, C, D, and so on, and what did they score for their well-being scale, as well as a percentage of conversations rated as deep talk. So in this case, we're looking at one individual who is measured for two different variables. And that's the important part here, is that we're measuring both of these variables because we're still looking at correlations. When we start into chapter 10, I believe, we'll be getting into experiments where we do manipulating, but for now, these are specifically measured variables. And then if we wanted to look at some other examples, we have this one looking at marital satisfaction. So respondent A, where did you meet your spouse, on or offline? And ratings of marital satisfaction. So we have two different variables here that were measured. In this case, we're seeing instead of sort of a scale, a continuous scale, we're having categories, but we'll come back to that with some of our discussions a little bit later on. And then another one here looking at individuals, this time with names instead of letters, giving us a score on a multitasking frequency test, as well as a task for a multitasking ability. So how often are they multitasking and how good are they at it? And so we can see some of these examples as we move throughout this chapter. And it's interesting to note here, so these tables are specifically set up showing us sort of one individual with two different measured variables. In conducting these experiments, the researchers may very well have collected multiple variables, not just two, but when we're specifically conducting a bivariate correlation, we're only looking at two of those measured variables at any one time. So just because you measured extra things doesn't mean that you can't do a bivariate correlation. It just means that you're choosing to look at two of them at a time. Now, if we want to start doing these bivariate correlations, how do we want to go about describing the associations that we're seeing? So if we have something like our first example where we have quantitative variables, where we have measured quantities, we could use something like a scatter plot. So our percentage of deep talk, so how often are they engaging in deep emotional conversations, graphed with their well-being scale. And so here, where they're saying that they're using Z scores, That just means that they've standardized their data. And so here we have each dot is a single individual who scored a certain amount for their deep talk score and a certain amount for their well-being score. So each dot in this scatter plot is a different person who got the scores that are indicated. And from where all of these dots are placed, we can calculate this line of best fit. It's going to give us the relationship between these two variables. So you can look at this graph and you can get a pretty good sense of whether or not this is going to be sort of a positive correlation or a negative correlation or no correlation. And in this case, we're seeing that it's positive, though it's messy. So we wouldn't expect this to be a very high R value. And in fact, our correlation coefficient, our R here, is only 0.28. So it's still a positive correlation, and there is a relationship here. It's just of moderate strength. It's not very, very high or convincing necessarily. And so if we're assessing the relationship here, we've seen one example, our scatter plot, but we've also talked about our other example, which is our correlation coefficient R. And we can actually calculate a correlation coefficient to get our value to go along with our scatter plot and our line if we wanted. Now, I am going to be showing you guys how to calculate R, and specifically how to calculate it in a couple of useful different programs, but I want to wait and do that until we're done chapters 8 and 9, because I want to go over bivariate and multivariate correlations before we actually start playing with some data and looking at conducting bivariate and multivariate correlations. So for now, we're just going to look at understanding R, and then we're going to get into the nitty-gritty of how we're calculating it and specifically what it's looking at statistically to understand how it's working. But that'll come a little bit later on, probably this week. So if we're going to sort of hand wave our calculations of R for right now, I'm going to give us a brief reminder of what an R value is telling us. So what is it that we're doing with an R value? So our R is going to give us an idea of, is it a positive or a negative correlation? Do we have a minus sign in front of it, making it negative? Or do we have no sign, or sometimes a positive sign, giving us this positive correlation? And that's just telling us the direction of the line. So positive correlation goes that way, and negative correlation goes that way, if we were looking at our scatter plots. And then we can have our strength of correlations. So sort of less strong to very strong. The closer to 0 we are, the less strength in that relationship. And so if we're close to 0, we're going to see a scatter plot where the line, or where the dots are very spread out. There's not a close relationship. Whereas if we had a higher score, whether that be high and positive or high and negative, the closer to 1 we are, ignoring that sign in front, is going to be indicative of a stronger correlation. So this is a much higher R value than this one would be. Let me clean that off. And we actually have a sort of mostly agreed upon standard for evaluating strength. So when a researcher is talking about, we got an R of this number, and that is a strong correlation, we kind of had to come up with a way to decide when we can say strong versus when we can say weak correlation. And this is where Cohen's guide for evaluating strength of associations for R come in. And this isn't agreed upon by everyone, but this is a pretty good standard to go with. So if you have an R of around 0.1, then we're going to call that a small or weak correlation. It's a very small or weak effect size. If we have somewhere around 0.3, then we could say that it's medium or moderate. And then if we're up to 0.5 or higher, then it would be large or strong. Now, if we've looked at this sort of graphic here, that's saying that anything in this range on either side falls into the high category. And you might think that that's kind of extreme because low and medium are all only in this little bit in the middle. But when you do, like when you practically calculate R, when you're looking at actual research data, you are very unlikely to see anything 0.5 or higher, which is why when you do see something in that range, it's okay to call it a large or a strong relationship, because what you're going to see most of the time is in these ranges here, the much smaller values. And that doesn't mean that it's a bad thing or that it's a poor experiment or it's a poor study. It just means that what you're looking at has a comparatively small effect size. And that's not a bad thing. So if we wanted to look at a couple of examples, so we've already seen this graph with our deep talk and well-being scale, and we said our R was 0.28. And so from our table here, we could say that that falls under a medium or moderate association. Whereas if we wanted to look at our multitasking people, so how often they multitask and how well they do at multitasking, this one is a negative 0.19. So if we put a line of best fit in here, it's going to look something like this, but we see that there's quite a bit of spread to our data, which is why it's a 0.19. So the negative tells us it's a negative relationship. The 0.19 tells us there's quite a bit of spread there. And if we're looking at this chart here, this gives us a good example where it kind of falls in between. And so we would talk about this as a weak or a weak to moderate relationship, because it kind of hits the middle of both. And that's, as someone who does research, I don't like the fact that it's not a clear cutoff. It's not a clean cutoff. So you could just say weak. You could say weak to maybe weakish, moderate. You wouldn't say just moderate. You have to include weak because it's still close to this one. But there isn't a clean cutoff where we wouldn't say it's weak until it hits exactly 0.3, because when we went back to 0.8, we called 0.8 moderate. So our 0.19, which is effectively 0.2, falls right in the middle, and it's weak to moderate. So maybe that doesn't bother you as much as it does me, but yeah, a small to medium association. Now, that's all well and good if we're calculating our R values and looking at scatter plots for two measured variables that have sort of continuous ranges. Continuous just being that we have numbers and you can kind of score anywhere on these axes. But what happens when one of our variables is categorical? So what if we go to that example of looking at marital satisfaction and where people met their spouse? And so our marital satisfaction is a continuous variable, or it is a quantitative variable where we have a continuous quantity here. But where they met their spouse, they have two options. They could have done it online or offline. And so that's going to be categorical. You're divided into two possible categories. And so if we set it up as a scatter plot, we end in this kind of weird situation where we just get two lines of dots. And you can technically report that. So we're saying here that, yeah, we have sort of this kind of a relationship. That's our line of best fit. And our correlation here, that's going to give us an R of 0.06. And that's a very tiny correlation. That is very small or very weak, which you can kind of get from looking at the data. There's not a really clean difference between these two groups. But this is not what you're usually going to end up seeing. In most cases, you're going to see something like this, where you can plot these results as a bar graph. So our categories are down at the bottom here, and instead of having the full range of the data, you end up reporting the group mean or the average. And sometimes if it's a really good paper, they could include something like error bars to show us how much of a spread there is of the data, to give us a better feel for what the data actually looks like. But that doesn't always happen, much to my anxiety, because I do enjoy my statistics and I'd rather they give you as much information as possible. But we will come back to error bars in the future. They matter just a little bit more. But this gives us a cleaner idea. We still have that sort of slight difference where the pinks are higher than the blues, but now we can just see it by comparing the averages. Now, if we wanted to tell the difference between our two groups, so if we weren't contented with just looking at our R, if we didn't just want to calculate our correlation coefficient, we could actually use something called a t-test. And we could compare the averages between our two different groups or our two different categories. And so if you're conducting a t-test, you're basically taking your first group, the people who met online, and asking if that group has a different distribution than the group that met in person or offline. So we're asking, is there a difference between these two different groups? And so your association claims you could use your scatter plots, you could use your bar graphs, you could use R tests, you could calculate your R, or you could do a t-test. All of these are going to still give you a decent idea of what's going on when you're looking at these associations. The part that we care about in distinguishing our associations from other kinds of studies is that an association claim, you're using two or more measured variables. So we don't care about the graph or the statistics you're running. It's what kind of variables are you working with. If you have two measured variables, then it's going to be a association, it's going to be a correlation no matter what. If we start looking at manipulated variables, even if we're using an R or a t-test, if there's a manipulated variable involved, it's no longer an association. That's when we get into experiments. So just to keep that in mind when you're looking at all of these different graphs and different charts and things like that, where the data came from is going to give us some information on how to actually interpret that information. So if that's what our association claims are going to look like, at least when we have two measured variables, now we're going to move on to how we can start thinking critically about these association claims, or using the textbook's terminology, how we can go about interrogating these association claims. And so we want to ask, so which of the four validities are we going to consider, and how do we go about evaluating them? Now, the textbook says that the ones that we care about most for an association claim are going to be our construct validity and our statistical validity. But we're going to talk about all four validities. We're also going to talk about our internal and external validities. They just matter less across more of the association claims. And we'll get to that. So if we start with construct validity, I've just reminded us of what each of these means. So our construct validity, we're specifically asking how well was each variable measured. And unlike when we were looking at our frequency claims where we just had one variable, here we now have two different variables to consider. So you can't just evaluate the construct validity of one of them, you have to look at both. We're also going to be looking at, does it have good reliability? Is it measuring what it's intended to measure? What is the evidence for its face validity, for its concurrent validity, and its discriminant and convergent validity? All the things. Is it doing what it's supposed to do? How well was it put together? So, for example, the MEL study that we talked about at the very beginning, where we were looking at deep talk and well-being, we could remember that they were using those automatic electronic recorders where people would code what people were talking about when the recordings were done. And then for the well-being measurement, they had a subjective well-being scale. So they were using some pretty well-established methods to look at those two different things. So we could say, if they're using a subjective well-being scale, something that has been tested and used in the past that seems to correlate well with measuring what it's supposed to measure, it's probably got good construct validity. And the same goes with their recordings, where they're using a random sampling of what people are talking about throughout the day, and they have multiple research assistants, assumedly, doing all of this coding, and they have certain keywords to look out for. We could say that there's probably reasonable construct validity there. Sometimes this is hard to get from different articles, depending on what kind of information you get in a journal. Very, very difficult to evaluate in, say, a media article. So if you were looking at construct validity from a newspaper article, I don't think it's going to happen. You're really going to have to go back to the source and hope that they published in a journal that encourages them to give more detail in their methods. But that's probably more than what we need to talk about. For our statistical validity, we want to look at how well the data that we've collected are actually supporting the conclusion that we're making. Now, this is going to be the biggest chunk of this chapter because we're going to talk about what each of these breakdown questions each mean. So if we talk about an effect size or statistical significance, we can look at outliers or restriction of range or curvilinear associations. Those are all theoretically new terms unless you've taken a stats course already. So we're going to break each of those down and talk about them individually. So what is the effect size? Effect size is describing the strength of an association. So some associations are going to be stronger than others. And for what we've been talking about, our effect size is pretty much going to be our R, our correlation coefficient. So the size of our effect is going to be the magnitude of our R. So how close to 1 is it? How far away from 0? So a large effect size would be on the larger size of things. Or we could use Cohen's chart, and a large effect size would be anything bigger than an R of 0.5. A small effect size would be closer to 0. And so we can look at these graphs here, and this one here, so they both have about the same line of fit running through the middle here, but graph A has a lot more spread to the data. The points are spread out quite a bit. So in this case, we would have a larger R. No, sorry, we would have a smaller R. Sure I say it right. A smaller R with a larger spread of data. So in this case, maybe we're seeing a 0.2. And then in this case, the data points are clustered much more closely to our line. So maybe our R is 0.7. And I'm just pulling these numbers out of nowhere. But given these scores, we could then decide that this is an R of small to medium effect, or a small to medium effect size, whereas this one would be a large effect, or a large effect size. And if we're going to talk about effect size, we might as well talk about what it means to have a larger or smaller effect size. And most of the time, pretty much all of the time, you're going to want a larger effect size because it's going to be more useful to you. So a larger effect size can give us more accurate predictions. Now, not all researchers are looking to do correlations so that they can predict information, but it is one of the traits that makes correlational research so effective. So if we look at this graph here, we're looking at this child, Hugo, and we wanted to see how accurately we could predict his height based on different factors. So we could look at Hugo's height at age 2, which is on this axis here. So how tall was he when he was 2 years old? He was 83 centimeters tall at age 2. Well, how does that compare to height at age 18? So when people stop growing. And there's actually, if we look on here, there's a bunch of points clustered very closely to that line, where if you know someone's height at age 2, you can get a good idea of how tall they should be when they stop growing at age 18. So here, Hugo stopped growing at 18. He was 170 centimeters tall. And from this line here, our line of best fit, the predicted height was 172 centimeters. And that 2 centimeters isn't really that huge of a difference. That was a pretty accurate prediction. And it's a pretty accurate prediction because our data points are clustering very closely around this line of best fit, or as they've called it, a prediction line. So this is just the line that runs through the middle of all of our data points as best as possible. And so the closer that these points are clustered to that line, the more accurate our prediction should be. And so, as we know, having points closer to the line means that you have a larger R, or a larger effect size, which is what we're illustrating here. Whereas if we switch to this next slide, so instead of looking at height at the age of 2, what if we were using our mother's height as our predictor? So if we know Hugo's mother's height, so she's 163 centimeters tall, then it would predict from that prediction line that the son's height at age 18 should be 174 centimeters tall. And that's still a pretty decent guess, but it was off by just a little bit more. So Hugo was actually 170 centimeters. And having a little bit more error here, a little bit less accuracy, comes from the fact that all of these points are a little bit more spread out. We have a lower R, or a smaller effect size. So this prediction was still pretty close, but it wasn't as accurate as the situation when we had a larger effect size. And this is just one example using a very small sample to make this prediction line, but you could imagine if you had more data, maybe you measured 1,000 people, then we might get better results. Who knows? This is just the example they give us. So the idea here is that when everything else is equal, so if there isn't anything else weird going on, a larger effect size is usually going to be considered more important than a small one. And now there are going to be some exceptions to this. Because when you hear that, you might think, okay, well then maybe we don't care about small effect sizes. Maybe we can ignore any of our small effect sizes. But think about medical research. So if you have a medical study that's looking at heart attacks and taking aspirin, if you have a small R, so one particular study ended up having an R of 0.03, which is a very, very small effect size. But that small effect size could still be considered important because of the number of lives that were saved. Because if we have a slightly positive correlation between surviving heart attacks and taking aspirin, then even if only a few people are helped by doing the act of taking an aspirin, that's still saving more people than no people. So if the outcome or the risk of not doing the action is very bad, like dying of a heart attack, then making that effort to take an aspirin might be worthwhile. So in this example, they had 22,000 participants in the study, 11,000 in the aspirin group and 11,000 in a group that didn't have aspirin. They were in a placebo group, which tells us right off the bat that this example is using an experiment, but we won't hold that against this example. It's still using R's, so it's still relevant. In that study, they found that there were 85 fewer heart attacks across the length of the study in the aspirin group. So even though it's a very small effect size, it still adds up to a lot of lives that weren't lost to heart attacks. So when the outcome is very extreme, something that's life or death, a small effect size can really matter. But if we're looking at something like height, a tiny effect size, we really don't care. If we could predict Hugo's height with an R of 0.03, then we really have no idea how tall he's going to be, and maybe we don't care anymore. But if we have a 0.03 correlation that might lead to saving a life, then it might be something that's worth doing. So that's one of the exceptions to having a large effect being the only time we care. So our next point to talk about is the idea of statistical significance. And this has been a long time coming to actually talk about this, because we've kind of mentioned it a little bit, but haven't really said anything about what it actually means. So when we're talking about statistical significance, we're talking about the conclusions drawn about how probable it is that a correlation of the size that we're observing would have come from a population with no correlation. So basically what we're saying is the correlation coefficient that we're seeing, is the association that we're seeing, is this relationship coming from pure chance, or is there actually something in that population that we're finding? So are we seeing noise in our data, or are we seeing something that matters? And so if we want to walk through the logic behind that wording, if we want to look into the logic behind this statistical inference, we can have the idea that we know already that researchers are collecting their data, they're measuring their variables from a sample, and by doing so, they're trying to draw conclusions about a larger population. So they're using a smaller subset of individuals to try and understand something about that larger population. So they're making an inference about that larger population. And an inference is a conclusion that's going to be reached on the basis of evidence and reasoning. So by collecting this data and running statistics on it. So if we find an association in our sample, we assume that the association also exists in the population. we can't measure the whole population. That's the whole reason why we're conducting, or why we've collected from a sample. And so when we talked about our different sampling methods and all of that sort of stuff, we kind of talked about this, where it's not reasonable to measure the whole population. So we're collecting a sample of individuals from that population with the hope that our sample is going to be representative of the population. But if we sort of flip that on its head, if there's no association in the population, assume that in the large population of interest, there isn't any relationship. There's an R of 0. There's nothing going on. But if through error, if through random chance, while we're picking our sample, we might accidentally find an association. So we might, by sheer chance, happen to find an association in our sample that doesn't exist in that original population. And so when we're looking at statistical significance, we're asking how likely is it to find that association if the population that we're pulling from doesn't have anything going on, if there's no association in that larger population. So to word it another way, our calculations of statistical significance are helping us as researchers evaluate the probability or the chance that the result that we're getting came from a population in which our association is actually 0. So how likely are we that we're finding something that doesn't exist? So when we use the term statistically significant, what does that mean? If we have a statistically significant result, what are we actually saying? So if we've calculated a probability estimate, or a p-value, which we've talked about before, and that p-value is very small, and we've said the cutoff is usually 5%, so a p of 0.05 or smaller, then we're saying that it's very unlikely that the result that we found, that the association that we found, actually came from a population that has no association. So if we got an R value of 0.2, and our p-value is very small, if it's smaller than that cutoff of 5%, then we're saying that it's not likely, it's very unlikely to get an R of 0.2 if the population you were pulling from had an R of 0. So we're saying that having a p-value that's smaller than 0.05 is significant because we are more than 95% sure that what we're seeing isn't due to random chance or weirdness going on when we're sampling. Now, if we look at the converse of that, what if we have a statistically insignificant result? What if our p-value is larger than 0.05? Well, if it's larger than 0.05, then we're actually saying that the chances are starting to get pretty high that there's a good chance that the result that we're getting could have come from a population that didn't have an association. So we're saying if it's insignificant, if it is not statistically significant, then there's a chance that we randomly got the people that gave us an R value that doesn't match our population of interest. So if it's statistically insignificant in our result, then we're saying that there's a pretty good chance that something went wrong when we were selecting our sample, and we ended up, by pure chance, getting a poor representation. And we can't be sure, we can't be certain that what we're seeing isn't just due to chance. Now we're going to be talking about statistical significance on and off throughout the rest of the course, and it's going to have similar but slightly varied meanings each time we're talking about a specific test. So we'll come back and talk about statistical significance again, specifically when we start looking at calculating our R's and interpreting tables for R's, as well as looking at t-tests. And then again, when we get into our experimental data as well. So p-values and statistics and our statistical significance indicators aren't going to go away. They're going to keep coming back. So don't be surprised to see them coming up again and again as we keep moving. All right. And then for our last thing that we want to talk about is this combination of effect size, sample size, and significance. So we just talked about our significance. That's when we're talking about our p-values. Effect size is our R values, or how strong of a relationship we're seeing. And then sample size is going to be sort of a involved factor, but a sample size is what it sounds like. It is the size of our sample. So this is really just the number of people that are in our sample. And so here we can actually look at how all of these points relate to each other. Now, in most cases, if we have a large effect size, say we have an R of 0.5, our cutoff for large effect sizes, having a large effect size, kind of regardless of our sample size, is going to give us a significant result. And that's just because this is something that has a high strength. And so even if we're only looking at a small number of people, we're usually going to see a significant result. And that's not always the case. If your sample size is teeny tiny, if you only had like 2 people, then we would have to reevaluate. But for the most part, a large effect size is going to be significant. But when we start getting into our smaller effect sizes, say we get down to a 0.1, then in order to get a significant result, in order to be sure that what we're looking at is actually something that's in that population, we would need to have a really large sample size. So if you had a sample of 1,000 people, then maybe you'd be pretty sure that when you get an R of 0.1, that it's actually something that you would see in a population. So you would be saying that, yeah, no, we have enough people that we're pretty sure that this isn't due to random chance. This couldn't come from a population with no relationship, with no associations, because we sampled so many people that we shouldn't be able to find this relationship in all of these people. Whereas if we still had our R of 0.1, if we have this small effect size and we only have a small number of people, we can't really be sure that what we're seeing is coming from that population. We could say that we are less certain, so our significance will be small. And again, when we start talking about actually calculating our R's and interpreting our p-values, we'll get some more examples of this there as well. But the idea here is if you have a large effect size, you're almost always going to have a significant indicator. So you're going to pretty much have a very small p-value for that, regardless of your sample size. But if you have a small effect size, we really care about our sample size because that's going to change whether something ends up being statistically significant or not. Our small samples, the ones that have a very small sample size, are a lot more easily influenced by chance events when you're choosing these samples. So you could, by chance, pick people that are going to give you this relationship, even in a population that doesn't have that relationship. All right. Now, we're talking about significance and calculating these things and sort of how we're going to get our R's and that sort of thing. But what does this actually look like when you're reading the research, when you're looking at a journal? How are you going to see these factors? How are you going to find out if something has a large effect size or if it has a significant association? What are we going to be looking at? And the answer is it really depends. So in some cases, you're going to get a table kind of like this. And so they're looking at different variables down here, and they're going to be showing overall correlation with well-being. So if they're saying here, this is our correlations, this is going to be our R value. So if we look down here, these kind of look like they match up with what we'd expect for an R. So none of them are larger than 1, and they can be positive and negative. That looks pretty good. So each of these indicators here, so this would be a correlation with well-being. So the well-being index and being alone, talking to others, small talk. So these would be some of the things that they measured, and this would be one of their measurements of well-being. So a measure of what kinds of conversations they're having and a measure of well-being. And what we care about here is, yeah, we have our R values, and that's telling us a negative medium association. But then we have these little asterisks. So if we look down at the bottom, they explain what all of their different symbols mean. And in this case, we are looking specifically for significance. And if we zoom in and look very closely at the screen, 1 asterisk means a P of less than or equal to 0.05. And they're specifying two-tailed, which we will look at when we start calculating our t-tests and things like that. But this is just saying that if our p-value is smaller than 0.05, so our normal cutoff for significance, it has 1 asterisk. And conveniently, there's one highlighted here that has 1 asterisk. So this one was significant, and so was this one here, and this one and this one. So you can go through and figure out which ones were significant at that 0.05 level. But what about these 2 asterisks? This is also giving us a p-value. And this one is saying a p of less than 0.01. So this is actually giving us a more strict cutoff. So I've mentioned before that our standard for statistical significance is going to be 5%, or that p of 0.05. But we could be even more strict than that. As a researcher, you could decide that you want to be even more certain that the result that you're getting couldn't have come from a population that didn't have this association. And so in that case, you could use a p of 0.01. So this is saying that there's a 1% or less chance that this could have come from a population that didn't have the association. So there is a 99% or higher certainty that what you are seeing is because the population of interest actually has that relationship there, because there's such a tiny chance that that population could have had no association. So the smaller the p-value, the more certain you are that you didn't get this result by chance. So the more certain you are that something is actually going on, that there's a real relationship here. And so we can see that these 2 asterisks points, they actually also line up with what we just talked about, where our higher R values, the larger magnitudes of R, are the ones that have 2 asterisks. So we're even more certain about the ones that have larger effect sizes. And we're less certain about the ones that are smaller effect sizes. And the ones that are really small effect sizes, they don't have any asterisks at all, which tells us that those p-values would be larger than 0.05. So these are ones where we can't be sure that there's anything going on there at all, because there's a pretty large chance that we could get those values even if there wasn't a relationship in that original population. So the ones that we're not certain of, they're not statistically significant, we're pretty much going to ignore those ones. And so we can direct our attention to the ones that have been flagged here conveniently by our authors. And now, not all charts are going to look exactly like this. Sometimes they'll include an actual a column at the side here that will give the specific p-value for everything that they measure. So they could list an individual p-value for every single thing that they calculated. So one column could have R's, and the next column could have the P's that go with those R's. And of course, as much as researchers like to try and follow some kind of rules or standardizations, journals aren't always going to use the same formatting. So you might see them labeled with just a P. You might see it labeled as a p-value. You might see the term significant or shortened to just sig. You kind of have to check what each journal uses. And so sometimes it's going to be pretty clear, like listing it at the bottom here, and other times you have to go hunting, but those are the different ways that you can see significance reported in a journal article. And I will tell you right now, you will almost never see any kind of report of significance in a media article because most media articles don't report statistics at all. They might say that there's an association between this well-being index and being alone, but they're not going to give you any numbers. So you're only really going to see R's and P's when looking at the actual scientific journals. Unless you are very, very lucky and happen to find a popular media article that is still somewhat scientific. But yes, you're only really going to see these in journal articles. All right, so moving on from our deep dive into statistical significance, our next question is all about outliers. And we can ask, could outliers be affecting the association that we're seeing? And so an outlier is going to be an extreme score, or maybe a couple of extreme scores that are going to lie very far away from the rest of our scores. So here, our first scatter plot has an extreme score. It has an outlier. This one dot is very, very far away from the rest of the text, or from the rest of our dots here. And our graphs A and B are identical except for this one dot. And so this dot goes along with a person who got 4 on whatever this axis is, and who got 15 on whatever this axis is. And so you can actually use this information and you could calculate an R. You could figure out what the association here is. And we can see what's going on. And so you could notice if we put in our prediction line or our line of best fit for each of these, having this point up here pulls this line just a little bit more steeply. And this is going to give us a different R value. So our R here might be lower than the R over here, because here all of our points are clustered really close around this line. But here, because this one outlier pulled our line upward, now all of a sudden we have more points that are further away from this line. There's now more spread just because the line had to move. So this can make our association, this can make our correlation weaker because this one outlier started moving things around. So these outliers can be really problematic, especially if an outlier is extreme on both measures. So if it's extreme in this case, getting a 4 on whatever this axis is measuring isn't that bad. So there's a couple of people here who have 4s. It's not a big deal. But this is an extreme value on this axis because now we have, the highest score before that was an 8, and now we have a 15. So that's only extreme on one axis, but imagine if this point was out here. What would it do then? If it's extreme on both of these axes, it can cause a lot of problems when you're calculating your R. And it can mess with your data pretty bad. Now, another way that it can be extra bad is if an outlier is present in a very small sample. So if our sample size is small, so in this case we have fewer dots, then you can notice that when we draw in our prediction lines, that this line is pulled up very high. It's much more influenced by this outlier than when there were lots of dots. And that's because as you have fewer dots to work with, as you have fewer individuals in your sample, each one point exerts more influence over the slope of this line. And so by having this correlation or this outlier, it can strongly influence your correlation, and it'll influence it more the fewer points you have to begin with. And when you're actually conducting statistics, if you identify an outlier, you can then sort of flag it for removal. You can run your statistics then without that outlier, and you can report what the results were with and without this extreme point when you're reporting it in your journal. So if you're writing something up, you can say that we had this one weird measurement and it caused a big fluctuation in the R that we had. And here's what the number is with and without this individual. Now we can take a brief moment and talk about where these outliers may come from. This could be an error. This could be maybe something went wrong with your measuring equipment. If somebody is filling out a survey, maybe this is a case where they were operating with a response set, where they were always saying yes to their questions. Or maybe this was something went wrong and their information was entered twice or something. Or it could just be that you do have an extreme case. Maybe you got, maybe one of these variables is height, and you got someone who is really, really tall. So sometimes these outliers are actual errors and should be removed, and other times they are useful data and you shouldn't remove them. And as a researcher, that you walk a fine line of knowing when to get rid of one or not get rid of one. And I have yet to find a good way to know when to exclude an outlier that everyone agrees upon. So that's an interesting factoid that our textbook doesn't go into, so I will move on from that. So our next thing to consider when we're looking at these relationships, when we're trying to interpret our statistics, is that we should consider if there is a restriction of range. And a restriction of range is basically when we don't have a full range of scores on one of the variables that's in this study. And so if your scores are, say, truncated, if we've cut them off too soon, it can actually make your correlation appear smaller than it really is. And so a fantastic example of this is looking at SAT scores. So the axis down here is SAT scores, correlating with the grades that people get in college, so the college GPA. And so on here, we can see that there's a general positive trend here, but it's not a very strong relationship because there's a lot of spread to the data. But if you know anything about SAT scores, which I actually did not at all, these scores can be much, much lower. So you can have an SAT score as low as, I believe, 400. And so what's happening here is this cutoff that's occurring at this 1200 mark is actually a restriction on the range because people with scores lower than 1200 weren't getting into the college that's doing this association. So if they're not letting people who got lower scores into college, then you can't measure the GPA that they get to look at the full range of scores. And so if we jump to the next slide, so we have the full graph here. So this is where that artificial cutoff was, this restriction of the range of SAT scores. And if the college doesn't let people in who score less than 1200, then this is the only information that you get. If we got colleges to let people in with lower scores, maybe they would score, on the same line as what we saw with our restricted range, but maybe not. And so here, if we kind of put in an artificial line here, you can see that there's quite a bit of space around here. There's lots of room, and this ends up giving us an R of 0.3. And then if we do the same line here, even though the line is longer, if we do the distances between all of the dots and that line right down the middle to calculate our R actually ends up being higher, up all the way to 0.5. So by getting rid of this restriction on the range, our R climbs. So we go from having a medium effect size to actually a large effect size. So having that restricted range can really severely reduce the R that you're getting. So how do you go about dealing with restricted ranges? In this case, you could have the college open up admissions and not use SAT scores to determine who gets into college and who doesn't, which I believe is what the case was here, where they let people in based on something other than SAT scores. It might have been grades in their high school, it might have been something else. But the college opened up admissions so they could get the full range. That's not always viable. In a lot of cases, a restriction exists for a reason. And so there actually exist some statistical methods where you can sort of backtrack and fill in where you would expect those points to be based on some predictive algorithms. And if you can do that, you can artificially unrestrict that range. And so those statistical methods do allow you to kind of fix the problem, and they give you a stronger correlation or a larger effect size. And sometimes that's your only option. If at all possible, though, you're much better off trying to recruit more participants so that you can actually fill in the range and get real data to fill in that restriction. But as we said, that's not always an option. Now, our last statistical consideration is to look for curvilinear associations. And so this is basically, you're going to find a situation sometimes where your correlation coefficient, where you have an R that's really close to 0, but the relationship between the two variables actually has a pattern. And so we can see an example of this down here, where we in fact see a curved relationship. So this is a curvilinear relationship. And so I guess we'll talk about the example that's here first. So this example is looking at the use of a healthcare system graphed against age in years. And so the idea here is that people that are very young, so children, will spend a lot of time going to the doctor. When you're younger, you have checkups every 6 months, every year, every so often. So you go to the doctor a lot when you're younger. But then once you get older, it's kind of expensive. Maybe you're too busy, but also you're fairly healthy, so you don't go to the doctors very often. And then as you get older, as you get over 60, you start going to the doctors again. So this relationship shows us a U-shaped or a curved relationship. Now, if we were doing a normal regression, if we were trying to calculate our R value, then we probably put a line kind of there and we'd get a 0, right? So this is an R of 0 because the points aren't linear, and so we can't get a good fit for our line. So if you had only tried to calculate R, if you had only sat down and pulled up SPSS or your preferred statistical program and you made it calculate R for you, if you got an R of 0 and called it a day, you might have missed the fact that there is actually a relationship here. It's just not what you were looking for. And so in this case, getting an R doesn't tell you anything about this relationship. But if you made a scatter plot like we did here, you could see very quickly that there's something else going on here. And from the statistics point of view, in a lot of cases, you can get around these curvilinear associations by adjusting one of your variables. Usually you can take the log of one of the two variables and it turns this curved association into a linear one so that you can actually go through your normal regression standpoint. But that's a little bit advanced, especially for this course. So just know that there are ways around that where you can still look at relationships like this, even if they aren't linear. All right, so if we have our statistics covered, we have our statistical validity evaluations covered, next we can move into our internal validity. And most of the time when we're looking at internal validity, we're looking at the idea of, can we make a causal inference from this association? And so as soon as we move past our frequency claims in the first couple of chapters, the textbook is basically trying to get us to the point where we can talk about experiments, because most research is done with the intention of establishing a causal relationship. And so when we're looking at internal validity, we're basically seeing how close can we get to making this causal inference, to assuming a causal relationship. And so we're going to start talking about our 3 causal criteria, the 3 things that will allow us to make a causal inference, where we can assume causation. And so these 3 things happen naturally when we get into experimental research, because we're manipulating things and we can make them happen. But when we're still looking at associations, when we're still looking at correlations, these causal criteria have to be evaluated sort of one at a time, and we aren't always going to see them all. So our 3 causal criteria are going to be covariance. So to have a causal relationship, we must first show that there is an association between what we think is the cause variable and what we think is the effect variable. So if we're looking at A and B, and I'm actually going to swap over to the next slide where we have a visual, because I find that this helps. So if we're looking at our covariance, we need to show that A and B are related to each other. If we want eventually to be able to say that A causes B, then we need to show that A and B vary together. They are co-varying. The next thing that we need to say is that there has to be some temporal precedence. So this is the idea of directionality. So if we're trying to get to A causes B, then we need to show that A comes before B. And so this is showing us that if we have sort of A and B are correlated, we don't really know if A caused B or if B caused A. So when we're just looking at the kinds of correlations we've been talking about, we don't really know which one came first. So it's very hard to infer causation because we don't have that directionality. Looking at our R's and getting our correlations does show us that there's covariance, so we can say yes to covariance, but we can't really do the temporal precedence. And our next one is another really big problem for us. And this is the question of internal validity, which is where we're at. And this is where we're starting to look at the third variable problem. So is there a third variable, we'll call it C, that's associated with both variables A and B independently? Is there something else that's driving this correlation? Is there something else going on that maybe we haven't measured yet? And so if there is a plausible third variable, if there is some other factor that we can think of that might be involved, we can't infer causation. So this is why we stress so hard that correlation does not equal causation, because we've kind of only got one of the three things that you need to get causation. Now, in the next chapter, we're still going to be talking about correlations, but we're going to talk about ways that you can use correlations to get closer to talking about causation, which goes against everything that you're ever told in statistics, but it kind of works. But we'll get to that when we get to that. So clean those off. So if we're talking about this third variable problem, this idea that there could be something else going on that's driving the relationship that we're seeing, how do we go about looking for this? How do we know that this potential third variable might be causing a problem for our internal validity? And so again, we can look at an example here. So both of these graphs are going to be different interpretations of the MEL study that we've already been looking at. So this is where we're considering how deep conversations that we have correlate with having a good well-being. And so if we ignore the colors for just a second, we have what we had talked about early on with, I believe, an orange graph where we have a positive relationship. So there is a positive relationship where the more deep conversations you have, the more subjective well-being you have. So you are going to be happier and feel more contented the more deep conversations that you have. And so that's what we've looked at already. But this time around, we want to start considering, okay, what could be a third variable? What else could be involved in having deep conversations and potentially feeling happier and more contented? And so we could propose the idea of, what about education? Could education level have something to do with both A and B, and then C would be our education? Ooh, that looks awful, but C is education. And so if we break down the data, these are going to be two examples of ways that this data could turn out. But we'll look at this one first. And so our blue dots are all centralized within this blue circle. And these would be our people with low education, maybe people who didn't go to university. And then our green dots are all going to be people that have a high education, maybe people who went on and got degrees, maybe multiple degrees. I don't know how they would have divided this. But in this case, the circles around these dotted lines are showing us what kind of relationship we're seeing for all of the individuals that fall within it. So here, if we only consider our blue dots, our low education, if we try and fit a line to it, we can kind of draw the line anywhere, and none of them are good. None of them are giving us a good relationship. None of them is a great best fit line. And so we end up with this problem where this is going to give us an R of 0 for the people who have low education, because as soon as we remove education, as soon as we take education into consideration, our relationship kind of disappears. And the same if we look at our green circle with our green dots in it, there isn't a strong relationship here either. And so what we're saying is that overall, the people with a higher education score higher on the well-being scale and higher on the number of deep conversations they have. And our low education have fewer deep conversations and score lower on that well-being scale. And so what we've said here is that by considering that third variable, by considering education, our relationship disappears. So this relationship, we can actually call it a spurious relationship between deep conversations and well-being, because that relationship only existed because of education. So if that relationship disappears when we take that third variable into consideration, then that relationship wasn't really there. And so this means that our experiment had very low internal validity because there was another variable, something that maybe we hadn't measured, that was driving the relationship that we thought that we had found. Now, if we consider this second case, so it's the same data, again, we're just kind of playing with it a little bit here. So the same idea of deep conversations and well-being, and our blue dots are still going to be people with low education, and this time the orange dots are people who are educated. In this case, we don't have perfect circles. Now we have these stretched out ovals. And so if we only look at our blue dots, we can actually still draw a decent best fit line. We're still seeing that there could be a best fit here, and we could still calculate an R. We could calculate an R of maybe 0.3 if I make up a number. And so what this is showing us is that our low educated people still show the relationship where the more deep conversations they have, the happier they are. And the happier they are, the more deep conversations they have. And that relationship holds true even for our orange dots. So they're both still showing a positive correlation. And so we can say here that even if we considered a third variable, the relationship that we saw didn't go away. So this third variable didn't affect our results really. And in this case, for this setup, our third variable wasn't a problem. We still have a very high internal validity because even when we took that other variable into consideration, the relationship persisted. And so now we can move on to external validity. And so as we've already talked about external validity at quite some length, we're looking at who can we generalize this association to? What other populations or other situations can we apply what we've learned to? And to do this, we can ask, how important is external validity going to be? And we want to look at if there are any moderating variables that could be going on. All right, so if we want to look at how important is external validity. Now, from what we've talked about already in terms of external validity, we know that we care very, very deeply about how we've obtained our sample. If you're looking at a paper and they're not using a random sample, and there isn't a good reason why they're not using a random sample, you should pretty much immediately reject the association that you're looking at. You should know that if it's not using a random sampling technique, that our external validity is probably really poor. Now, sometimes you can run into a situation where we know that it wasn't conducted using random sampling, but we don't want to apply the study broadly. Maybe you had to use the snowballing technique and you're only looking at people who have Crohn's disease. Well, if you're only trying to apply your research to people with Crohn's disease, then that's probably okay. But that is something that we addressed in the last chapter. When we're trying to get our ideal situation, where if at all possible, we're going to be using random sampling, then if you don't find random sampling, you're going to be very suspicious of the results. So the first big thing you have to care about with external validity is where is your sample coming from and how does that compare to the population at large. So we're going to look at another one of the examples we mentioned early on, which is the multitasking example. And this is the idea that people who multitask more often, who spend more time multitasking, tend to do less good at it. And so we're only going to consider these, let's consider the yellow dots for now. And we can use our ovals to show us that there's a negative relationship. So the idea that if you spend more time multitasking, you do less good at multitasking. But in this case, unlike before, where we were looking at just all of the data all at once, here they've split it up with O meaning older adults and Y meaning college students, because I guess they didn't want to say young adults. But in this case, we're seeing that even though our older adults are scoring lower on both axes, so they score lower on the multitasking score and they score lower on the time spent multitasking, we're still seeing the same relationship. So we're still seeing that negative correlation, and the slope looks fairly similar. The spread of the data is fairly similar. So in this case, even if our original sample was only older individuals, or if it was only college age individuals, by checking it out against another population, we're saying, yeah, this isn't so bad. This isn't immediately causing us to be concerned about the external validity. We just want to keep some things in mind. However, if we ran into a situation where maybe instead of this oval being the exact same as that one, giving us the same slope, what if our older individuals were showing the opposite relationship? What if this oval, the yellow oval, looked like that? And so now we have two different R's from the different subsets of the population. That would be telling us that we have very low external validity because the relationship changes dramatically depending on what part of the population we're looking at. So you can kind of take a step back and consider how does the sample that you have compare to the rest of the population. And most of this is going to be a big question of, did you use random sampling or not? All right, and then our last point is all about moderating variables. And so when the relationship between two variables changes, depending on the level of another variable, then that variable that's causing the changes is the moderator. So we have a neat example here that I hadn't actually considered until the textbook pointed it out. But in this case, we're looking at sports teams and how many people attend the games of the sports team versus how many wins the team has had that season. And so the idea here is that in a lot of places, if your team is doing really well, then more people are going to go to the games. And so we would expect then if, your team is doing well, so more people attend the games, we get a nice, strong, positive correlation. And that's what we see in one city. So in Phoenix, Arizona, with their baseball team, as the team does better, as they perform and win more games, more people come to the games. But that's not always the case. If we look at Pittsburgh, in Pittsburgh, our relationship actually looks a little bit like that, where it's a slightly negative relationship. And so the people looking into this relationship wanted to know what might be driving this difference. What is moderating this difference? And here, the moderator is actually the residential mobility, which is basically how much are people moving into and out of the city. So in Phoenix, they have a high residential mobility. So people move into the city, they move out of the city, they don't stick around long, and therefore don't have any particular loyalty to the team. So when the team starts doing well, they figure, I might as well go and watch because they're doing well. Whereas in Pittsburgh, there's a low residential mobility. People don't move to Pittsburgh, and people don't move away from Pittsburgh. And so because people stick around, that's the team that they grew up cheering for. That's the team that they are fans of. So they're going to go and watch their favorite team, whether they're winning or losing. And so in this situation, this residential mobility, this whether or not people move to or from this city, is a moderator for the relationship between the success of the team and how many people attend the games. And there's actually graphs here that are a little bit clearer than my scribbles, showing that positive relationship in Arizona, and that positive relationship coming from that high residential mobility, and that slightly negative relationship in Pittsburgh that's probably moderated by that low residential mobility. And so that is a great example of a moderating variable. And that brings us to the end of understanding bivariate correlations. So as promised, in our next lecture, we're going to get into multivariate correlations. We're going to start looking at more than two variables, and excitingly, looking at ways that we can get closer to making a causal claim even when we're using correlations, which is super cool. So I will see you guys then.